know you feel the vibes.
What's up, guys? Welcome back to another Algebra 2 instructional lesson here with Mr. Gaines as we continue our discussion on PF.2 zeros in graphs of polynomials. So where we left off in the last notes video in part 3, we had graphed problem 10a, a quartic polynomial. It's blank here on the screen, but we did graph that one. So if you have not gotten to that point, make sure you watch part 3 and then come and finish up here. So we're going to go ahead and continue on part B. The instructions here were to sketch a graph of the polynomial, including the correct X and Y-intercepts. So we're going to start with the Y-intercept, because this polynomial is in standard form, and so it's pretty easy for us to find the Y-intercept. All we have to do is essentially substitute in 0 for X, and that would give us a positive 27. So I'm going to go ahead and put that point on the graph. If you wanted to show that work, you definitely would be able to show that work by just showing here that we substitute in 0 for X. Let me get the correct notation down. And that's going to be 27. So anytime you want to find the Y-intercept, you just substitute in 0 for X. So I'm going to put a point there on the Y-axis because the Y-axis is not labeled. And then I'm going to label this as positive 27. Now I want to go ahead and take a look at the end behavior of this function. So in order to do that, I need to take a look at both the leading coefficient and the degree of the function. So the leading coefficient we see here is a negative. So again, that tells us what happens for the end behavior on the right of the function. This function, it is going to go down to the right. So I'm going to put a little arrow there in the bottom right to remind myself that when I draw in my path that I need to be going down there to the bottom right. It is an odd degree. We see this exponent of 3 as the highest power here. So odd degree tells us that the ends go in opposite behavior or opposite direction. So over here on the left, we will be going up. So once I get my Y-intercept and my end behavior, now I can focus on getting my X-intercepts. So remember, X-intercepts can be found by setting the function equal to 0. So I'm going to replace g of x or y with 0. And I'm going to work on solving this. I may notice that because there's 4 terms in this polynomial, I might want to try to solve this by grouping. So I'm going to group x, a negative x cubed and negative 3x together. And I'm going to group the 9x and the 27 together. Then I can take a look at the method again of factoring by grouping. So I'm going to factor out the GCF. So if I factor out the GCF, I'd still have my 0 equals. The GCF I may take out of the first one. Sorry, this should be a 3x squared there. We can hardly see the function, but that is a negative 3x squared. My GCF for my first group should be x squared. I'm going to go ahead and make my leading term there positive. So I'm going to factor out a negative x squared. So that would leave me with x plus 3. And the other group, I'm going to factor out a positive 9, which would leave me with x plus 3. So at this point now, I can take my 2 factors that are, or my 2 coefficients, and I can group them as a factor. So this would be a negative x squared plus 9 times x plus 3. I can factor this a little bit further. I'm going to go ahead and do that. At this point, you could set both equations equal to 0 and solve. I'm going to factor a little bit further and factor out a negative here of my first pairing, my first group, which would leave me x squared minus 9. And my x plus 3 I'm just going to keep here for the time being. In doing so, I may notice that I have a difference of 2 squares. So what I can do there with that x squared minus 9 is factor that into x plus 3 and x minus 3. So if I factor this into x plus 3, and I already have another x plus 3, I can go ahead and write this as x plus 3 squared and x minus 3. So again, my x squared minus 9 factored into x plus 3 and x minus 3. Because I had another x plus 3 here, I left my x plus 3 as squared. So then my zeros, if I take a look at this factoring here, my zeros would be x equals 3 by setting x minus 3 equal to 0. And x equals negative 3 by setting x plus 3 equals 0. One thing that we want to make sure that we notice here is that for x minus 3, that this factor occurs twice. And so the graph is going to change directions there at x equals negative 3. It's essentially going to bounce off of the point x equals negative 3. So I can go ahead and put in these points on my x-axis. My x-axis is labeled there, so I've got a point at negative 3. And I've got a point at positive 3. And then I can go ahead and sketch in my curve. Again, we are going to bounce off of the negative 3. So it's going to go up to the left, and I'm going to sketch it as best I can with this technology I have here. It's going to go up to the left. It's going to bounce off at x equals negative 3. It's going to pass through that y-intercept of 27, come down and pass through the x of x equals positive 3, and finish going down to the right. So as we sketch this, again, I don't have the greatest technology here that I'm sketching with, but as we sketch this, it should bounce off of negative 3 in a kind of a curve, not really a V-shaped, but a curve pattern. So now we have a graph that shows our y-intercepts, our x-intercepts, and the correct in behavior. Let's go ahead and consult the calculator and see what the calculator shows for this graph. So I'm gonna have this graphing technology. You guys are gonna have that available to you to help you on assessments. We do need to make sure that we're showing our work, but we can also use this to check our graph in this instance. And so as we do so, we see that our graph is very similar to the graph that's shown here. The window is a little bit scaled on the y-axis, so let me scale this y-axis up a little bit so we can see that y-intercept, and now this looks a little bit closer to what we have on our graph. Okay. Now again, we didn't find the relative maximums or minimums, so we don't know exactly where this graph is going to turn and change direction for this maximum point, but we have displayed the correct x-intercepts, the correct y-intercepts, and the correct behavior. Let's go ahead and take a look at another example. So taking a look here at C, we have a similar situation going on. So we want to first find the y-intercept. And so the y-intercept again would be by taking 0 and substituting it in for x, and in doing so we would come up with negative 12. So we have a y-intercept here of negative 12 that we can go ahead and plot on our curve. So we can get that point down there. And we want to go ahead and label this as negative 12 on the y-axis. Now we want to make sure that we include the correct in behavior. So if I'm taking a look at the leading coefficient is positive, which means on the right side of this graph, I'm going to be going up for my in behavior. The degree is an odd number, which means on the in behavior, I'm going to be going in opposite directions. So the left, I will be going down. Now to find the factors, or to solve this problem here and find the zeros, the x-intercepts, we may want to take a look at this and we say, okay, there's an even number of terms, and I might want to go ahead and group them. But what I may notice here is that if I were to take out a GCF, it would be x squared in the first set of parentheses. That would leave me with x plus 2. There's no way to take out a factor in the second set of parentheses that would leave me with x plus 2. So grouping this with the first and the last is not going to work. I could try to reorder my terms and set up different groups, and I'm going to find that no pair here, the way that it's written, no pair is going to allow me to group this effectively. So grouping is not going to be a method that's useful for this polynomial. Now there are multiple methods we could go to at this point, but one of them that we have discussed and we have frequented in this topic has been the rational roots theorem. to identify any possible rational roots that it could exist for this function. Remember, the rational roots theorem tells us that any potential rational root or x-intercept would come from taking the factors of the constant, in this case negative 12, over the factors of the leading coefficient, in this case 1. So I would have 1 over 1, 2 over 1, 3 over 1, 4 over 1, 6 over 1, and 12 over 1. Both positive and negative cases of those numbers, as each of those numbers are factors of 12, and the factors of my leading coefficient would just be 1. So one of these numbers has to be a 0, or sorry, if a rational 0 for my function exists, it has to come from one of these listed numbers. So what I can do here is I can go ahead and substitute in these values for x to come up with, or to see if that solution is going to be 0. So I'm going to try positive 1 first, which would be 1 cubed. Really, I wouldn't need to put in those 1s because just 1 times anything is going to be 1. So you can just type in the coefficients and add and subtract those. That's a lot easier. But if you want to type in all the 1s for x, you can do that as well. And what we would come up with here is that 1 would not be a viable option as a 0. So then I could go on. I could try negative 1. So negative 1 replacing for x, so negative 1 cubed plus 2 times negative 1 squared minus 11 times negative 1 minus 12. Essentially what this does is changes the signs to of the coefficients for anything with an odd power. So this would become a negative 1, this would become a positive 1, and so on and so forth. And we would find out that negative 1 would be a 0 here. So what I'm going to go ahead and do is I'm going to go ahead and put negative 1 on my graph, because I know that negative 1 is a 0, and that's going to be an x-intercept. So I'm going to go ahead and put that point down. But I also need to find the other x-intercepts. And so this is where synthetic division comes in. This is the process that we've used prior to this for finding zeros of a polynomial of a greater degree. So I'm going to take this negative 1, which is a 0. I'm going to complete synthetic division between negative 1 as my 0 divisor and f of x. So I'm going to take my coefficients here for f of x, which would be 1, 2, negative 11, and negative 12. I don't need any 0 placeholders. All coefficients are accounted for here. And I'm going to go ahead and complete the process of synthetic division. I already know that my remainder should be 0, so I'm going to go ahead and put that 0 in there. And if it works out that way, then I did everything right. If it does not work out that way, then I did make a mistake. So let's go ahead and let's complete synthetic division just to make sure that negative 1 is a 0, and to give us a place to move on from there. So remember, we add in the process of synthetic division, we add down the columns. So in this first column, there's not going to be anything to add. So I'm going to go ahead and just bring down my 1. Get my value set up here. So I'm just going to bring down my 1. Then I'm going to take this 1 times my 0, which is negative 1. And I'm going to multiply those together and put that in the next column. So 1 times negative 1 would be negative 1. That goes in the next column. Add down that column. So 2 plus a negative 1 would be positive 1. And then take this negative 1 times 1, which would be negative 1, put that in the next column. Add down that column, and I would get a negative 12. And take this negative 12 times negative 1, which would be positive 12. That goes in the next column, and add down that column, and I get 0. So again, the reason that we do this is because it allows me to rewrite f of x as the product of the factor x plus 1, which gave me the 0, negative 1, which we already used, and then this coefficient here, or sorry, this quotient here, which would be x squared plus x minus 12. So the x plus 1, we already went ahead and we dealt with that. We worked with that factor, so I'm just going to leave that there for now. And I'm going to solve again for f of x. So let 0 equal f of x, which is x plus 1. And then I may notice that x squared plus x minus 12 does factor rather nicely here. It factors into two binomials. We know that the first term of each would be x and x because they have to multiply together to give me x squared. I should know that the factors of a negative 12 would yield me one positive number and one negative number. And then the factors of 12 that would work in this would be negative 3 and positive 4, because if I distributed through there, I would come up with a positive x. So this is the complete factorization here for f of x plus 1, x minus 3 times x plus 4. So my zeros then for x would be negative 1, which we've already found. I'm just listing it again. 3, coming from the factor x minus 3 if I set it equal to 0. And negative 4 coming from the factor x plus 4 if I set that one equal to 0. So I can go ahead and plot these points on my graph. I've got negative 1. I've got positive 3 here. Change the size of this point. There's positive 3. And there's negative 4. And now I can sketch my curve. So I know that each one of these zeros occurred one time, so it's going to pass through each one of these. It's going to finish going down to the left. So I'm going to go down to the left. I'm going to pass through negative 4. I'm going to turn and pass through negative 1. I'm going to pass through my y-intercept of negative 12. I'm going to turn and pass through, get a draw here, pass through positive 3. And then I'm going to finish going up to the right. So now I have a graph displaying each of my x-intercepts, my y-intercept, and my in-behavior. As always, let's go ahead and type this into the graphing calculator to check. So again, my graphing calculator is going to be a little bit more accurate than the work that I have done here. But I want to make sure that I put in my picture to make sure my in-behavior is correct, my x-intercepts are correct, and my y-intercepts are correct, and I have the general shape of the graph. And if I look at the standard graph, that looks pretty close. Let me expand this window. So I'm going to increase my y max and y minimum. I'm going to make this a negative 15, positive 15, just to get a little better picture there. Now take a look at my graph. And this looks pretty similar to what we have displayed here. Okay? So we have displayed a graph with the correct x and y intercepts, the correct in behavior. Again, a relative maximum and some minimums we're not too concerned about at this time. If we need to find those, we'll find them on the graphing calculator. Finally, one more function to complete here. If you're getting the hang of this, go ahead and take a moment and see if you can complete problem D here. Let's pause the video and complete problem D and see if you get the same results that I get. Alright guys, so hopefully you were at least able to get part of this one done, if not the entire thing. So let's go ahead and let's catch up to where I got to this point in time. So I went ahead and started by finding the y-intercept, substituting in 0 for g, which gave me a negative 12. I plotted that negative 12 and labeled it on the y-axis. I identified the in-behavior. The leading coefficient is negative, meaning I'm going to go down to the right with an even degree. It has a degree of 4, so both ends are going to go the same direction, so I'm going to go down to the left as well. I took a look at methods here to factor this quartic polynomial. It's not a trinomial, so I can't break it down into two binomials, and it doesn't group. So I went to the method of finding possible rational roots. And so you can see here that P over Q is the possible rational roots for g of x, which is the same ones that we used in f of x on C. It's not always going to be that way, but because my factor and my leading coefficient are relatively the same other than positive negatives, my constant leading coefficient, the possible rational roots are the same. I also identified, you can see my calculator here, that negative 1 is going to be a 0. I have not plotted that 0 yet. I'll come back to that in just a little bit. But I listed negative 1 as a 0 and went through the process of synthetic division. So hopefully you were able to get through this far. Now the process of synthetic division left me with, g of x here that is now going to be equal to x plus 1, which is the factor that gave me negative 1 is a 0, and negative x to the third plus 1 x squared, or just x squared, plus 8x minus 12. And generally what we would do is we'd focus on this negative x cubed plus x squared plus 8x minus 12 and work to try to find a solution or zeros for that piece, to factor that. And I may look at that and think, okay, I can group that. But if I went through the process of trying to group, I would find out that that factor would not work either. So what I'm going to do here in this case is I'm going to go back to the possible rational roots theorem. And I'm going to try to find a secondary possible rational root. So if I get to a place where I've used a possible rational root, I found that it's a 0 through the remainder theorem, and then I used synthetic division to come up with another factor. If that other factor, in this case, negative x cubed plus x squared plus 8x minus 12, we do not know how to solve for, I could go back to that possible rational roots theorem and try to find one that works for this expression. So I'm going to go ahead and use the next option, which is 2. So I'm going to substitute in 2 here. So I'm going to use this x cubed plus x squared plus 8x minus 12. So I'm going to do negative 2 to the third power plus 2 squared plus 8 times 2 minus 12, and that does come out to 0, so 2 is another 0 of this function. It's not the only other one that exists, but it's another one. So what I'm going to do here is I'm actually going to get rid of this expression that I had for g of x. I'm going to get rid of that altogether, and I'm going to go back to my quotient that I left off in with synthetic division. Now you can draw a completely new synthetic division expression here if you want to, but I'm going to go ahead and just continue this one. I'm going to continue a secondary path of synthetic division here. So I'm going to put my my positive 2, if I can get this to right here. I'm going to put my positive 2 on the outside. There we go. Now I got it doing what I want. I'm going to put this positive 2 on the outside of this synthetic division. I'm just going to continue working with the quotient that I had previous to this. So I'm going to put now a positive 2 outside here, because this is going to be a new 0 that we're adding into this expression, where we have found that works for g of x. And I'm going to complete synthetic division with this positive 2 and our quotient that we were left over with. Again, you can create a whole another separate division division symbol and rewrite the quotients, but I'm just going to continue since they're written here. So I found negative 1 is a 0. It gave me a polynomial I could not factor. So now I went back and I found another 0 that was 2. And now I'm going to use that 0 to come up with a quotient for what was left of g of x. So I'm completing the process of synthetic division again here. Sorry guys, it's taking so long to get set up. But I'm going to drop my negative 1. I'm going to take that negative 1 times my 0, which is 2. So negative 1 times 2 would be negative 2. That goes in the next column. I'm going to add down that column. Negative 2 plus 1 would be negative 1. And I'm going to take that negative 1 times 2. That goes in the next column, which would be a negative 2. And then take 8 plus negative 2, which would give me 6. And take my 6 times 2 and put that in the next column. Give me 12. Add down this column. And 12 plus negative 12 would give me what I would expect to have as a remainder here, 0. So now g of x can be rewritten here. G of x can be written as x plus 1. My factor that gave me negative 1 is a 0. X minus 2, my factor that gave me 2 as a 0. And now negative x squared minus x plus 6. I'm going to go ahead and factor out this negative of the third term, or the third group that I have here, the trinomial at the end. So that's going to give me g of x, which equals, I'm going to put the negative out in front, x plus 1 times x minus 2 times x squared plus x minus 6. So we should notice that we can factor x plus squared, sorry, make this a little bit bigger here, run another room. We should be able to notice that we can factor that final term there, or that final expression. So we still have negative x plus 1, we have x minus 2, and then x squared plus x minus 6 would factor into x plus 3 and x minus 2. So I could then notice I have two x minus 2's, so write this as x minus 2 squared. So finally, after all of that work, my solutions for g of x would be negative 1, which we found initially, 2 for x minus 2. Notice that it's going to bounce here because this happens twice, and negative 3. So we had to go in this problem here, we had to go through the process of using the rational roots theorem, possible rational roots theorem twice, go through synthetic division twice, and then finally we can factor to get to the very end. So I need an x-intercept at negative 3, I need one at negative 1, and I need one at positive 2. Again, it is going to bounce at positive 2. Should go down in both ends. So I'm going to have it going down here from negative 3, go through negative 3, go through negative 1, pass through my y-intercept, turn around, come up to positive 2, bounce off positive 2, and finish going back down to the right. And if I graph this, take a look at this in the graph. Again, our scaling's off a little bit, but we can see something similar to this. We pass through 3, pass through negative 1, go through the y-intercept of negative 12, and bounce off 2. So we have displayed here a function with the correct x-intercepts, the correct y-intercepts, and the correct behavior. So this is our goal if we have to graph functions algebraically. Now we're not always going to graph functions algebraically. Let's go ahead and take a look at problem number 11, where we're going to look at these functions, but graph them from more of a technology, use of technology and technological perspective. So, in problem 11, it says, in the year 2000, Mark and his wife Maria decided to invest some money in precious metals. As expected, the value of the investment fluctuated over the years. Through 2008, the value of the investment was modeled by V of t, where V of t represents the gain or loss in hundreds of dollars in year t, where t equals 0 is 2000. So we're tracking this investment of precious metals from 2000, our starting year, to 2008. And it's going to follow this function, V of t. In part A, it says sketch a graph of the function. So what we're going to do when we get into application problems is we're not really going to test our algebraic skills. We're going to try to use the technology to help us. So what I'm going to go ahead and do is I'm going to go ahead and I'm going to graph this function. So I'm going to type in the function but use x instead of t. So this would be x to the 4th minus 11x to the 3rd plus 38x squared plus 38x squared. Boy, cannot type in anything correctly right now. Minus 40x. And I'm going to graph this. Again, we know that this is going to start at the year 0, which is 2000, and we want to track it through the year 2008. So I'm going to hit window, set my x minimum to 0 to start at year 2000, and my x maximum 8 to finish at the year 2008. Then going to hit zoom and go down to the 10th option, zoom fit. What that's going to do is fit my picture onto my graph. And so this is roughly the picture that we see. So we see that it starts slightly below the y-axis. It goes above the, it starts slightly below the x-axis. It goes above the x-axis. Looks like it dips back down below the x-axis and goes back up. Let me cut my window down just a little bit, just to kind of see that. Cut it down to 100. And yeah, we do see that kind of pattern in here. So it says to go ahead and sketch the graph. So we're going to go ahead and sketch this picture that we see here, drawing in my labels, or labeling my function as I draw it in. Okay, so there we have a rough sketch of the graph. We have some labels for the axes. Now we can use this graph to answer the question. So it says, first in B, find the years when their gain or loss was 0. So gain or loss would be the value. So basically we want to find when the value is at $0. And we can see on the graph there are 3 locations. If I'm looking for that here using the graphing calculator, I'm going to hit second and trace. That's going to be 0. So there's 3 of them. First it's going to ask me left bound. So I want to move the cursor over to the left of my first intersection. So it's hard to see here, but I've got the cursor down somewhere in this area on the graph. I'm going to hit enter. It's going to say right bound. So I want to move my cursor over to the right. Again, it's a little tough to see, but I have my cursor somewhere around here on the graph. So it's to the left of the 0, to the right of the 0. And then it's going to say guess. I'm not going to guess. I'm just going to hit enter. And so this gives me the first 0 here. So I'm going to go ahead and plot this point on the graph. And this is essentially my replacement for algebraic work. Now, if you wanted to do this algebraically, you would find these zeros. We're not going to do that, but you could find these zeros and algebraically, and you would show that work. I'm just going to go ahead and list these zeros. So this first one right here, let me get that typed in, is 2, 0. I'll just type in the coordinates for that point, place that in the right location, label my graph, and that is my work here to find that first 0. I'm going to find another one, so I'm going to go back to my calculator, hit second to trace, take the 0 option. This time it says left bound. I'm going to move it to the left of my next 0 and hit enter. It's going to say right bound. I'm going to move it just to the right of that 0, hit enter. It's not going to say to guess. I'm not going to guess. I'm going to go ahead and hit enter. And that's going to give me my new point here, and this point is for 0. So I want to make sure we label that point again on the graph. And finally, find the last one. So second, trace 0, left bound. I'm on the left side of this final intersection, hit enter. Right bound, I move to the right bound of that final intersection, hit enter. I'm not going to guess, just hit enter. And it gives me the last one here, and this is 5, 0. So I need to take these points and then interpret them. Remember, we're looking for year when the gain or loss was 0. So the years this is years since 2000, so 2 would be 2 years since 2000, 2002. 4 would be 4 years since 2000, 2004. And 5 would be 5 years since 2004. No, sorry, since 2000, so 2005. So I can go ahead and answer that question based on the labels on my graph. Now it says, in what years was the investment worth less than they paid? So we can take a look at this graph here and we can see anything that's below the y-axis is less than what they paid. So we can tell that initially this graph starts below and stays below until it intersects the x-axis at 2002. So we can say that between the years of 2000 and 2002, and between the years of the next step beneath the y-axis or the x-axis would be 2004 and 2005. The graph was less, or sorry, the value was less worth less than what they paid. So the next thing that we can do is go on and to answer question D. What was their gain or loss in the year 2008? This does not come from the X-Intercepts. The last two questions we were able to answer by finding those zeros on the graph. This time we want to know the year 2008. So let me extend my window back to what it was. So we want to find the value in 2008, or the value when X is 8. So what we can do here is again go back to second trace to the calculate menu. Now we need to find the value for an X value. We know the X value is 8. So I can go ahead and type in 8 and it gives me my answer here in coordinate form. It does not give me my answer to my question, but it gives me the coordinate that's going to answer my question. So I'm going to go ahead and put this point on my graph. Again, it doesn't have to be exactly perfect, but we just want to essentially display where we're getting our answer to our question from. So 8, 5, 76 is that point, and I'm going to put that point on the graph. That's just there, which is really towards the top of our function. And it says what was their gain or loss. Remember, this is the value. Maybe value was not the correct term to use here. Maybe I should have labeled this as gain / loss. So the gain or loss in hundreds of thousands of dollars would have been $576,000. So this would be $5.76 million. So based on this graph in 2008, they probably should sell because they're at a profit of $5.76 million. So again, these things can be found algebraically. You could have solved for V of t by working through the process of factoring to come up with these zeros, and then answer questions B and C based on those zeros. Or you could have substituted in 8 for V of t to come up with the 5.7 or 576, which we then put back into context. So you can do those algebraically, but in some instances, especially finding the zeros here, it's probably a lot easier to do these graphically. So anytime we're not forced to do them algebraically, we're going to go ahead and sketch a graph, label that graph, and use that graph to answer our questions. This looks like a good place to stop for PF2. Sorry it was a little bit longer here with the lack of technology here, but hopefully you guys get a good idea of how to graph by hand and then how we can use our technology to help us graph and solve questions. In class on Monday, when we reconvene, we will go ahead and go through problem number 12 and then cover any questions that we may be having on homework or practice. As always, thank you guys for tuning in, and I'll see you soon.